All right, so now let's take a look at part two. Part two, we're going to substitute and state the domain. Okay, substitute, substitute, and domain. All right, so we noticed that in part one we had this h in the constraint nicely isolated, so we can make a nice substitution here. So let's go ahead and do the substitution. The surface area as a function of r is now going to be 2 pi r squared plus 2 pi r. Now instead of h, we're going to substitute the value of h that's written in terms of r here, which is 64 over pi r squared. Okay, 64 over pi r squared. So now we have just one variable that's a function in terms of one variable that is easy to differentiate, okay? All right, so let's go ahead and simplify this resulting function. We're going to have s of r is equal to 2 pi r squared plus um, going to simplify to 128 over r. So basically you have the r cancel, this r goes here once, so this r goes here once, and then this pi cancels out with this pi, and then 2 times 64 is 128 over r. Okay, so this is our surface area function in terms of r. Okay, next thing we have to do is we need to state the domain of this function. So let's write it down, domain. So this is the function and then domain. Now, first thing you can notice off the bat is that there is a r in the denominator here, which means that r cannot be 0. Okay? Now, can r be negative? Let's take a look at the situation. We're dealing with uh, the measures of a figure, namely the radius of a cylinder. Can a radius have a negative measure or negative value? The answer is absolutely not. So we know that r cannot be negative, r can only be positive. Okay? So we know for one thing that r has to be bigger than 0. Now how big can r be, or how small can r be as long as it's bigger than 0? Now if we get infinitely close to 0, um, what happens is that this term right here gets really, really small, and this term dominates. As r approaches 0 from the right, this term approaches infinity, and this term approaches 0. So this term dominates. It gets infinitely large. Okay? Now, if r approaches infinity, what happens? If r approaches infinity, this term goes to 0, and this term dominates. It gets infinitely large. All right? So what does that tell us? It tells us that there are no constraints on r as long as it's bigger than 0. So our domain is r is greater than 0, or you can write it as 0 to infinity. Now, what does this tell us? It tells us that r is in an open interval. It's not a closed interval. Hence, the endpoints are not going to be considered when looking for extremas because there aren't any endpoints, all right? Okay, so there goes the function and the domain, part 3. What we're going to do now is we're going to find the extremas, okay? Extrema. The potential extremas, because we do not know yet until we do the classification. All right. All right, so for potential extremas, what we're going to be looking for here are the critical points and endpoints, okay? But since the endpoints are not valid in this problem, it's an open interval, all we're just going to look for are the critical points. Okay, so let's go ahead and do that. What we're going to do is find critical points. So find the critical points. Now, what are the critical points? The critical points are where f prime. Well, in this problem, we're dealing with s, right? So let's call it s. So in this case, critical points are where s prime is equal to 0 or s prime does not exist. Okay? So those are the values of r that we're going to be looking for in this part of the problem. Okay, so let's rewrite the function under consideration. We have, let's see, s of r is equal to 2 pi r squared plus 128 over r. Now, let's differentiate this function. But before we differentiate it, we can rewrite this portion so it's easy to differentiate. I don't want to use the quotient rule if I don't have to. So this is going to be can be written as 2 pi r squared plus what? Plus 128 r raised to the negative 1 using the reciprocal property of exponents, okay? Now it's easy to differentiate simply by using the power rule. So s prime of r, so for the first portion here, 2 pi r squared, we take the derivative, that will be 4 pi r, and then the derivative of this will be, is in the power rule, this minus times this positive will become minus 1 times 128 r, and then we decrease this degree by 1, so minus 2. Okay, so we can rewrite this as 4 pi r minus 128 over r squared. Now let's combine these two. I like to write my derivative as a numerator and denominator so we can know exactly where it's equal to 0, the numerator, and where it does not exist, which is basically the denominator component. All right, so put this over 1, and let's unite them. We need to find the LCD, times this by r squared top and bottom, and our derivative as prime of r in combined form is going to be 4 pi r to the third minus 128, this entire thing divided by r squared. Okay, all right. Now, remember, when we're looking for the critical points, we need to break the problem up into two parts, where the derivative is equal to 0 and when it's non-existent, okay? So we're going to find where s prime of r is equal to 0, and then where s prime of r does not exist, all right? So let's do the first one. So when you're looking for where the derivative is 0, you can simply just extract the numerator and set to 0, and that will suffice. So because if you set the whole thing to 0 and you cross multiply, what happens to the denominator? The denominator gets cancelled out because r squared times 0 is r. So let's forget that step and just set the numerator to 0, okay? Now if I move 128 to the other side, I have 4 pi r cubed is equal to 128. Divide both sides by 4 pi, and we'll have r to the third is 128 over 4 pi. And if you divide top and bottom by 4, this will give you 32 over pi. And then when you take the cube root, you're going to end up with r is equal to the cube root of 32 over pi. So that's the only critical point that we have. I'm sorry, the only point where the derivative is 0. Critical points that involves the non-existence of the derivative, we have to set the denominator to 0 because that's what makes the derivative undefined. And we know that wherever the derivative is undefined, we have a critical point there. So what we're going to do is set r squared equal to 0. That's the denominator. Take the square root of both sides. We'll have r is equal to 0. Okay? So should we consider this in our problem? The answer is no. Do you know why we are not going to consider r equals 0? Because it's outside our domain. Remember, we said that r cannot be 0 because it's going to cause our area to be undefined right here. So in our domain restrictions, r has to be 0 or greater. And we have a critical point where r is equal to 0. Since it's outside the domain, we're going to drop this off, okay? So this one violates our domain constraint, so we're going to drop it off. All right, so this is the only critical point or potential extrema that we have. All right, so what we're doing in this problem is we're looking for the minimum. We're trying to find the least amount of material. So let's classify this. We're going to do a classification. Now, if we can show that this is a minimum at this point, then we have accomplished our goal. All right, so let's classify. Now, we're going to use a second derivative test. If a point is a minimum, then the concavity has to be upwards. Okay, and if the function is concave up, that tells us that the second derivative, s double prime, has to be positive. So if the second derivative is positive, here at this r value, then we're confident that this is in fact the minimum, okay? And then that's the value that minimizes the area. So let's do the second derivative test. Basically, we're looking for f double prime has to be greater than 0, okay? That implies upward concavity. All right, let's do that. So we have the derivative function s prime of r. I don't remember what it is, so let's scroll a bit. Where are you? Okay, let me use this form right here. So 4 pi r square. So it's going to be 4 pi r square minus 128 r to the negative 2. Actually, just 4 pi r. So 4 pi r, 4 pi r minus 128 r to the negative 2. So we're going to differentiate that again. Scratch this out. All right, so let's differentiate that again. So the derivative is going to be the second derivative, s s double prime, s double prime of r is going to be 4 pi, because the derivative of r is just 1, minus, factor this out, 128. The derivative of r to the negative 2 is going to be negative 2 r to the negative 3. Okay, and then when we simplify that, we're going to have s double prime of r equals 4 pi minus times minus is a plus, plus 128 divided by r to the third. Okay, so just by looking at this, what can we conclude? Just by looking at this function, you notice that for our domain constraint, r is always bigger than 0. Okay, so since r is always bigger than 0, if we plug a positive number in this expression, what's going to happen? S double prime is going to be positive. Okay, so since r is greater than 0, s double prime of r is always positive. Always, it's always going to be positive. We don't even actually have to check it, because this expression shows us that is whatever value of r we plug in, as long as it's positive, the resulting answer will be positive. So s double prime is always positive, hence s of r is concave up. It's concave up at r equals the cube root of 32 divided by, so what did we get? 32 divided by pi. So it's concave up there, okay? And a minimum exists here. Okay, so by second derivative test, the second derivative is, if the second derivative is positive and you have a critical point there, that critical point is going to be a minimum. All right, so that's the kind of situation we have. All right, so that's basically the value that we're looking for here. Now we're going to shift to part 4, where we're going to state our conclusion. All right, so let's state our conclusion. Part 4, conclusion. All right, so for this part, well, we know what h r is. We're asked to state the dimensions of the steel of the cylindrical tank. All right, so we know that r is equal to the cube root of 32 over pi. And what is the height going to be, though? What is h going to be? We know that we found out earlier in the problem that h was equal to, h was 64 over r squared. Okay, h was 64 over r squared over pi r squared. That's what we had earlier. remember when we were looking for the constraint function in terms of h, we have this. So now let's plug in the value of r into this function right here. So to get what h is, all right? So h is equal to 64 divided by pi times the cube root of 32 over pi square. All right, so let's go ahead and simplify this. To make it easy to simplify, how about we express everything in terms of uh, cubes? Now, cube roots to be specific. Now you notice there's a 32 here, so I can factor out a 2 out of this top numerator so that it's consistent with this 32 right here. So I want to write this as follows. So factor out a 2, and then 2 times. Now let's express, if I take out 2 from here, I'll be left with 32, but I can write 32 as 32 to the third power raised to the 1/3. Okay, 32 to the third power raised to 1/3 is just 32, same thing. And then on the denominator, pi can also be written as pi to the third raised to the 1/3, right? Because they just cancel out. And in this business right here, I can write it as 32 over pi raised to the 2/3. So the reason why I did this is I want all the denominators of all the fractions to be identical. Basically, I want them to all be threes, okay? So if they're all threes, I can factor this out, and I can write it as 2 times, um, 2 times 32, right, it's 32 to the third power, 32 to the third power over, let's see, pi to the third times 32 square over pi square, the entire thing raised to the 1/3. Okay, what did I just do here? What did I just do? I just took out the 1/3 power from all three terms. Okay, and then this square right here, I distributed to the 32 and also to the pi. Okay, so what happens with this setup? What happens is that, see this pi square cancels with that, and then this 32 square just takes out one of these powers right here, and what are we left with? We're left with 32 times uh, 32 over pi raised to the 1/3, right? 32 over pi raised to the 1/3, which is equal to 2 times the cube root of 32 over pi. Okay? Now, does this look familiar, though? Does that look familiar? It should. This piece right here is the same as r. Okay? So it's basically equal to 2r. So that's basically what it is. R is equal to 2r. All right, so dimensions of our the dimensions of our cylindrical tank. All right, so let's write it down. The dimensions of our 64 cubic feet cylindrical tank that holds the least that uses the least material material has a radius of the cube root of root 32 over pi and a height of double that, 2 times the cube root of 32 over pi. Okay? And if you want to find the approximation of this, you can plug this into your calculator. And the approximate value, you can write it like that, or r is approximately 2.1677. I'm going to put the units there, feet. And h is double that. If you double that, you get 4.3354 feet. Okay, so there goes your answer. This is the exact value, and this is just an approximation of the results. Okay, so that's that. And thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking subscribe here. And please post a comment to let me know what you think about this clip. And do give me a thumbs up if you liked it. I appreciate it. More clips can be found on notgoodserve.com/calculus. Thanks again for watching and have a wonderful day.